Ladies and gentlemen, let's get into the video. As I hinted at just a few days ago, we scored an interview with AMD concerning high bandwidth memory, concerning TressFX, concerning Vulcan, concerning DirectX 12, and a few other bits and bobs. This is going to be a couple of part interview because we've decided to do it in a back and forth manner because I think it makes for a better interview, quite frankly. So we're going to jump right into this. Obviously this is an article as well if you want to go ahead and check it out, because we do provide links to certain subjects as well as some graphics and other bits and bobs. So if you prefer this as a written rather than me reading it out, then that's your prerogative. Anyway, as I said, the link's in the video description. So let's get on with it. As you'd expect, I will... if I need to make a side note, I will point it out so everything's verbatim from what Robert says, and when I'm speaking I will say that, it's me. Okay, so from us, can you tell us why high bandwidth memory is so important for next generation GPUs such as the Radeon 300 series? We all know about the Fury X, the VG / whatever you wish to call it, so I figure that's a pretty good question. Robert responds, it really comes down to three issues: performance, power and size. GDDR5 has been around for about 7 years and we've been wonderfully productive technology in that time, but it's reaching a point in its life where additional Mbps of bandwidth consumes a disproportionate amount of power. That's poor equation for client devices, for example CPUs, GPUs and SoCs, where your fixed amount of power consumption has to be balanced between ASIC, we'll tell you what that is in just a second, and DRAM power. If you can't get enough wattage to the ASIC because the memory has started to consume too much of the total, then the ASIC performance will start to begin to fall over time, and nobody wants that. We can solve that with HBM. HBM resets the power performance curve on DRAM by more than 7 years, as it's over 3.5 times more power efficient. I also mentioned performance. The direct outcome of faster ASIC is a larger demand for more bandwidth from memory, and those demands will quickly exceed what GDDR5 is technically capable of. Providing an ASIC generations progress, computing is all about pushing back bottlenecks, and I think HBM paves the way for that. Faster graphics engines that would otherwise be data starved with GDDR5. Finally, form factors. People appreciate smaller devices, and a chief way to make the GPU smaller is to reduce PCB complexity. GDDR5 memory chips, traces and power circuitry consume a considerable area on the PCB, and your bus width is effectively determined by how many chips you have at a 32-bit chip. So if you make the board smaller or less complex, by eliminating DRAM you sacrifice memory bandwidth. HBM solves that problem by collapsing all of the DRAM alongside of the ASIC and a single module known as the interposer, and all of that area on that GDDR5 is used up is now freed. So what is ASIC or ASIC? People pronounce it different things. It's technically pronounced ASIC, but I've just got a bad habit. It's a custom designed chip for specific purposes. You can basically substitute it as GPU, you can substitute it as CPU, it is that. Now basically, in a nutshell, what Robert is referring to here is quite simple. Memory requires power to operate. Memory is not free, although we might think, oh, it's just a bit of memory on the board, that's not going to make the difference. It actually does consume power. We'll get more into that in just a second in terms of the amount, but it does gobble up energy, and that energy, because obviously there is certain amounts of TDP that you don't really want to go over because of either cooling, because of power consumption. You don't want to plug in a thermal nuclear reactor to power the bloody GPU. You've got those concerns, so effectively lowering the amount of power that the memory requires means that you can instead divert that power to the GPU, the actual processor, which means that you can get more performance. This is particularly true when we're not dealing with die shrinks. Obviously when things do go down to, for example, 16 nm, that's going to be good, but even then, if you've still got GDDR5, which is consuming a lot of power, and more power is consumed, the more bus width you've got because you've got more chips on the PCB. Pretty simple. But anyway, moving on. How did AMD become involved in the project for high bandwidth memory, and could you tell us of their role? Or your role, more specifically. Robert responded to the little known fact that AMD is a huge player in the memory space. Joe Macri is Vice Chairman at Large on the JDEC Board of Directors. JDEC, as a slight aside, they are the Memory Standards Commission, effectively. And AMD was behind the initial proposals for GDDR3 and 5, and now HBM. In a very real way, AMD engineering and proposals have set the tone for PC GPU memory for over a decade. In creating a technology, like GDDR5, naturally we're also able to innately familiar with the strengths and weaknesses over the long term. As GDDR5 was entering the market on retail devices, we were already starting work on HBM as the eventual successor that would solve the long-term challenges and move the CPU industry, or GPU industry, another big step forward into the memory space. And 7 years later, here we are with HBM. I don't really think that requires me to go too deep into that one. I think that's pretty self-explanatory. Is GDDR5 memory currently bottlenecking, I ask, high-end GPUs, for example, the R9 290X? Yes, technically there are GPUs which are faster in AMD's lineup, for example, the 95X2, but effectively they're just stacked and they're still using, split channels and all that stuff, so I figured it's best just to ask about the 290X. Or is HBM more a preemptive, future-proofing measure? Robert responds, there are certainly applications out there that specifically benefit from greater memory bandwidth, especially fill rate limited scenarios. It's one of those days, isn't it? But performance scaling across resolutions also benefits from greater memory bandwidth, and as 4 and 5K come into the scene in force, that scaling becomes more and more important. I ask, that HBM doesn't rely on extremely high clock speeds like GDDR5 and instead relies on ultra-wide buses, 1024-bit, to provide its additional performance. Could you elaborate as to the reasons behind this? I think many of us are aware of this stuff, but once again, I think it's good to ask this stuff at the base and get, AMD's take on it. So anyway, Robert Hallock responds, high clock speeds aren't bad, but they aren't explicitly good. High-frequency GDDR5 has taken the graphics industry to 320 gigabytes per second in an age where it's needed, but high frequency costs power, and high frequency also costs complexity. It takes more silicon and more electrical devices to build memory and controllers and power circuitry that can reliably sustain the higher clock speed. GDDR5's higher clock speed is a virtue of per package pin count, where each GDDR5 chip only offers 32 bits of bandwidth. So you have to gang lots of chips together, then run them at high frequencies, QDR signaling to reach an appreciable bandwidth figure. As a slight aside, I'm going to say this now, so out of Robert's quote, this basically means that let's assume that you want a fairly wide bus width. Let's take the example of 256-bit. That would mean that you're going to require at least 8 chips, 16 for high. It could be 16 depending on the width of the bandwidth. So depending on bus width, and obviously then you've got the clock speeds as well. So with all of that plus the additional circuitry, that's basically what he's referring to. Getting back into the quote, if you want to build a technology that runs at a lower clock speed and to do it without sacrifice, then you can definitely do so. Our solution was that you want a high-speed manufacturable interposer. The interposer is something of a silicon motherboard through which we route incredibly dense traces, trace density that can't be done on a normal PCB. Out of quote, traces you can think of as just wires, basically. The solder on the motherboard. It's very basic, but that's kind of where we're going with this, simplifying the stuff. Getting back into the quote, and with that density you can put as many stacks of HBM that offer a 1024-bit memory interface. You can build multiple stacks, each with 1024-bit interface, and because your bus width is so wide, you can now afford to run a much lower and more power-efficient frequency. You can also use the tried and true DDR clocking, which reduces complexity all throughout the product. Overall, it's very advantageous for HBM to run at lower frequencies it does. So I ask, in one of your press slides, all of this is available in the article, you'd mentioned developing high-volume interposer solutions which the stacked HBM and other GPUs or processors sit on. Could you explain how or a little of what interposers is? We've already kind of gone through some of the stuff in the previous answer, but anyway, Robert says, and I quote, And I just realised a typo in my own article. Luckily, I haven't published it yet. I touched on the interposer very heavily in my previous answer, but it's worth pointing out that the interposer is not not a new idea. What it is new, and what AMD did invent, is an interposer suitable for high-performance ASICs. We've already discussed what they are, GPUs. Back into quote. Past designs from other companies have been small devices like FPGAs, basically low-power devices. An interposer isn't the challenge, though, it's the solution, he says. This is tremendous need for and desire to integrate disparate functions into a discrete chip or package. Over time, we've seen the trend: north bridges, south bridges, graphics, PCI Express, voltage regulation, caches. All of this has been brought into the processor over time. Why? Because it benefits power, size, and performance, the holy triester. Now, DRAM could definitely use the benefits of integration too, but the process used to make DRAM not compatible with the manufacturing process on magic logic chips like SOCs or GPUs. Holy crap, it's difficult to read all of this stuff without pronouncing anything wrong. Anyway, continuing. So if you cannot integrate in the way that people expect, example on die, then you find a way to integrate the interposer. The interposer allows for the integration of very different logic and DRAM processors with an on-chip power, size, performance benefit. You can use the right manufacturing techniques or nodes for each type of component and then stick it together like Lego. I think that's pretty well explained, actually. Okay, I continue by asking, because of the power requirements for HBM, is it fair to say that it will work extremely well in a wide variety of devices, including low power devices such as ultra-thin laptops? Robert responds, we haven't announced any specific plans. HBM does apply across our product portfolio, and HBM is a great help of any device that could use a better balance between the ASIC power, DRAM power, and bandwidth at a given wattage. Which, out of quote, pretty much a lot of them, let's just be totally honest. For a modern GPU such as the R9 290X, how much power is consumed by the GDDR and how much will be saved by HBM? Robert responds that they're not actually ready to talk about specific wattages yet, or power, but the HBM does use 50% less. Can you give us any insight on how long AMD and its partners have been working? And they have already answered that, but I'll keep the question in anyway for those who are skim reading, and that, of course, is the initial proposals for AMD were written about 7 years ago. Vulcan. So it's my understanding that AMD provided a lot of code for Mantle towards Vulcan, and some of the tech industry dub it as Mantle 2.0. Why did AMD decide to push so much of its code towards the project? Robert responds, Mantle changed the world. Game developers were in great need of PC graphics APIs that allow better control and better hardware performance than what's available. Developers saw how much they could get done per T-flop on console, and they've always had a LL API. LL stands for low-level API, and greatly designed something like that on PCs. They went around to every GPU vendor, but AMD answered the call and delivered a solution, Mantle. Many months ahead of anything like it, Mantle was in development and launched over 3 years before another contemporary appeared. It's been a stated goal of ours to transform Mantle into an industry standard, or spawn a set of standards that behave like Mantle. But our contribution of Mantle to the Kronos group, we achieved both goals. Now, Vulcan certainly builds on Mantle and extends it to hardware and operating systems that Mantle never supported, and the Kronos Group has worked very hard to make Vulcan a uniquely powerful API, and AMD cannot take credit for what is done beyond our contribution to jumpstart the effort. But we are proud that they saw the value of our work and agreed that Mantle was indeed the right foundation. Despite inaccurate reports to the contrary, Mantle also lives on and evolving as a standalone API. Out of quote for a second, this part is quite critical and I'd highly recommend you pay very close attention. For example, it's the hidden nucleus for our Liquid VR project. Fast, responsive, and interoperable virtual reality is the new frontier of our industry. Just how draw calls were back in 2013/14, and we're putting significant effort behind establishing ourselves as the go-to platform for VR in hardware and software. We are also continuing our discussion with multiple vendors on utilizing Mantle as an innovation platform for select partners with custom needs. I can't say much more than that at this time. We've also done a Vulcan analysis, incidentally, out of quote from Robert. If you want to go ahead and check it out, it's linked once again in the article, which is linked in the video descriptions. I put a link within a link so you can be linked while you link, and all of the general meme stuff. So what about True Audio? What about TressFX? Because let's face it, they were being pushed quite heavily. TressFX saved a lot of GPU performance, I ask. TressFX 2 rather saved a lot of GPU performance. You might recall that TressFX 2 was included in the the remastered Tomb Raider, and the original TressFX was included in the original PC release. Robert responds that TressFX 2 was a huge step forward in performance and quality. We added new support for grass and fur, continuous LODs for performance scaling and distance for players' perspective, improved performance of many light sources, self-shadowing and depth, modular and open code with porting documentation, and some tweaks to the physics model to make it feel more lifelike. We're on the verge of TressFX's free arrival, and it is incorporated in the Dawn engine, which is powering Geos X Mankind Divided, the upcoming DirectX 12 ready game we're working with Eidos Montreal. TressFX 3 brings improvements to collision, shape preservation, stretchiness, wind effects, anti-aliasing, and translucency. AMD True Audio is particularly salient in the new world of virtual reality, with three-dimensional auditory cues must align with three-dimensional visual cues. It's very disorientating when those two scenes are mismatched, and AMD alone offers the hardware-software solutions to unite the two at high speeds with ultimate quality. And that's all I can say for now. So anyway, hopefully you've enjoyed the video. Thanks very much to Robert and AMD for their time. There will be a follow-up, hopefully, to this interview over the next few days, maybe a week or two, depending, obviously, on people's schedule, because Robert's extremely busy and we're pretty busy as well. But hopefully we can continue to pick his brains a little bit regarding graphics technology, because I think it's pretty interesting stuff. I've learned quite a lot. And also we've got a few other interviews coming up as well, including from a couple of games developers, which should be kind of cool. Doing a bit of a closey thing, if you will, regarding virtual reality and so on. I'm really excited about the technology personally. I've said before, and I'll say again, that my first impressions of virtual reality were not that favourable when I just read about it. I honestly did not think it was going to be too cool. I didn't think it was going to be something I was going to enjoy at all. And it was only when I actually got the development kit 2, obviously of Oculus Rift, and I actually tried it myself on Half-Life 2, that I realised that it was a really cool piece of technology. And there's only been a few instances that I can remember I've been that impressed. One of them was when I played the Sega Saturn back in the day, played Virtua Fighter. And of course, you know, the graphics by today's standards are very primitive, but to actually have a port of the arcade version in my home, when I loved Virtua Fighter, on a couple of instances I got to play it when I was really young at an arcade, and then now it's actually in my home, it really impressed you back in the day. And another instance was actually with the original Half-Life, when I invited a friend round. Literally the second I bought a Voodoo 2 card, I installed it, invited him round, and we played the game in, I think it was glide mode. I don't think it was OpenGL or Direct 3D. I believe it was originally just supported glide, and it was just astounding. It was just one of those moments. And virtual reality for me, when I played Half-Life 2, and I just loaded up a random save and just looking around, like it was an indescribable feeling, and I think it's going to be a lot cooler. And I'm for any technology which can reduce its latency, which can improve reaction time, which can improve the audio, and obviously a lot of companies are striving towards it right now, so I think that's very good indeed. But Hopefully you have found the video helpful, informative, interesting, combination thereof, or perhaps something else that I didn't quite use an example of. But anyway, if you could do the likey, commenty, subscribey thing, I'd be extremely appreciative. But for now, I'm going to get going. It's fairly late here in the UK, basically midnight, so I've still got to do editing and all of that jazz. But hopefully you've enjoyed the video. I'll see you soon. Bye for now.